Welcome back to the workshop. We're going to continue on in section 9.1, dealing with sequences, with the limit of a sequence. Now, the limit of a sequence, again, is a limit, so we're talking about limits, and we're looking at as n goes to infinity. So as we continue on and let n get large, what do the terms in the sequence approach? And we would say that the limit of a sequence is some real number L, so not positive or negative infinity. So the limit of a sequence is some real number L if a sub n becomes arbitrarily close to L. Okay? This is no different than the definition of a limit of a function. Okay? If the function becomes arbitrarily close to the value, the limit is that value. It's the same case for sequences. So we would say that the sequence converges if the limit exists, and we would say the sequence diverges if the limit does not exist. So there's a couple different situations, or a few different situations. If the sequence has values that oscillate and just continue bouncing back and forth between values and not eventually flattening out. If it just continues to go up and down, then we would have an oscillating sequence that does not converge. You could also have a function that goes off to infinity, or a sequence rather, or a sequence that goes down to negative infinity. Of course, it can oscillate between those as well. So those are the different situations for convergence and divergence. Essentially, limit exists, limit does not exist. So let's take a look at a few examples, the same examples that we took a look at in the previous video. But in this case, we want to find the limit of the sequence if the limit exists. Okay? And we want to comment whether the sequence converges or diverges. So in the last video, we noticed that this sequence takes on the values. Let's see here. We saw that it was 1/2, 2/3, 3/4, and we could continue on to see that it's 4/5, 5/6, 6/7, and so on. Now you could just look at what these terms do and say, oh, this is what I believe that the limit is. The limit exists and it happens to be whatever you believe it is. Okay? And that's perfectly acceptable. In its most basic sense, that is exactly what a limit is and how it can be thought of. So in this case, we can say that the limit as n goes to infinity of n over n plus 1 is equal to, well, what would it be? It'd just be 1, right? They keep getting closer to 1. And we would say the sequence converges. A sub n converges to 1. Excellent. So what about our next sequence? In this case, this takes a little bit more time to think of here, but we found that the terms look something like, let's see here, oh, you know what, I actually made a mistake in our last video. I think I forgot to subtract 1 in all the numerators. I just realized that now. That's okay. Effectively, it doesn't change in terms of our convergence. It would change what our values were in the sequence, but not in the convergence. So we should find that it's 0, and then 2 squared minus 1 over 2 times 2, so that should actually be 4 minus 1 over 4, so 3/4. So it's 0, and then 3/4. Yep, and then 3 would be 8 over 6, and then 4 would be 15 over 8, and 5 would be 24 over 10, and 6 would be 35 over 12. Some of these you can simplify, other ones you cannot, but this kind of starts to give us an idea of what the sequence looks like. All right, so the question is, what is the limit as n goes to infinity of n squared minus 1 over 2n? And in this case, we actually have that the limit it does not exist, right? The values are going off to infinity. So we would say that the limit does not exist, and we would say that the sequence a sub n does not converge. Excellent. So what about part C here? All right, so this gets into our recursively defined sequences. So this one, it might not be so obvious for us. But if we recall the values that we found them to be, well, of course, 32 is the first value. Then we have 16, then 8, then 4, 2, 1, 1/2, 1/4, and so on. So in this case, since we're always taking half of the previous term, and we start with something positive, we know that we're always going to be positive. But because we're always taking half, we also know it's going to get smaller. So it's going to get smaller and smaller and smaller, but it's never going to go below 0. So in this case, we can be confident that the limit does exist and that it would be 0. So the limit as n goes to infinity of a sub n, we can just leave it in this format here. The limit of the sequence is 0, and the sequence converges to 0. Excellent, that's not too bad. And then finally, for our last example, again to a recursively defined sequence, we found the sequence to be defined, or having the terms 0, 1, 1, 2, 3, 5. We could continue on to find that it would be followed by 8, 13, 21, 34, and so on. So we could continue on with that as well. But what we notice quickly is that these numbers just keep increasing quite quickly, in fact. So the limit in this case would not exist. We'll call it f sub n. The limit as n goes to infinity is, well, it does not exist. So the sequence f, the Fibonacci sequence, does not converge. Excellent. So we'll take a look at more sequences in just a little bit. A quick note that this situation here, where we took a look at a sequence that appeared to be decreasing in values, but also stayed above a particular value, above 0, we'll take more of a look at that in a later video regarding section 9.1 sequences. So I'll see you guys again here in just a few minutes, back in the workshop, working on sequences.